Well, it's a pleasure to be here today. This talk will, I hope that we'll spend a little less time on the very broad views, although I have several slides that show some very broad pictures of things. But also, it's my intention to get to some examples of some very specific technical issues that I think are critically important for developing this general area of carbon sequestration, especially with negative carbon. So I'm going to go through some of these pretty quickly, but a couple of things that I want to focus on there are two issues that I think are critically important that have been talked about in nearly every talk this morning, but I want to emphasize them. One is that the efficiency of a process is got to be one of the most important figures of merit if you're talking about carbon capture, and I want to focus on why that's so important and how that figures into the grand plan. But the other thing I want to mention is that economics are important not just from the standpoint of people who are dyed-in-the-wool capitalists who want to make money, but if the economics of any energy conversion system become too bad, the whole system actually starts to fail. I'll just give you a couple of examples. The least economically developed nations in this world are also the most environmentally damaged nations in this world because there isn't enough excess in their society to do anything about the environment. But it's not just the developing world that has that issue. If you look at Europe, for example, where just a couple of years ago even, there was far more enthusiasm for carbon capture and global warming than there is now. And I would argue that the principal reason for that is the economic downturn and the lack of enthusiasm people have for investing more money into something that they don't see a real economic return from. So both for developed and developing nations, so the bottom line is what we need to focus on are sensible, practical things that are reasonably economical and efficient. And that actually figures prominently into some things. So enjoyed very much the talk just 3 talks ago, I guess now, that these are actually slides from the IEA version of that same report that we were talking about. But I come to a couple of several similar conclusions, but a couple of different conclusions. One of them is that what this shows is if you use biomass for trying to capture carbon, this is the amount of carbon you can capture depending on what technologies you use, but you can't add these together. So the first and most important thing here is that the limitation in all of these processes is the biomass supply. It's not the ability to sequester CO2. It's not even the ability to transport the biomass. It's the availability of biomass itself. And so in any one of these technologies, if you co-fire biomass with coal, you could they break this out into several different analyses, but the technical potential of sequestering CO2 is about 10 gigatons of CO2 equivalent per year. Or you could do that in circulating fluid bed, or you could do that in IGCC, carbon capture, and you can see several of the other potentials here. But you can only do one of those. You can't do all of them. There's not enough biomass to do all of them. And so if you go through here and ask the next question, which of these are the most realistic, which are the most efficient, and which are the most economical, the picture changes dramatically. This is something we can do essentially today, and it's actually almost cost effective, not really quite cost effective. By contrast, this dedicated biomass process with an IGCC is something that I'm not too sure we'll ever be able to do at the same kinds of efficiencies and the same kind of costs that we can do these other things. So when you make these kinds of choices, you have to keep that in mind. And similarly, you look at the energy potentials. If you look at the total down here, the biomass resources are estimated at, we saw some of these numbers, but if you, the biomass resources are 65, 42, and somewhere between 20 and 35 exajoules per year for crops, ag residues, and forest residues. And one of the things I would point out, and this is something I talk frequently about, is if you add the total residues available, which are materials that are not going to affect food supplies, they're not going to affect other kinds of economics, they're not going to require additional agriculture, which has a significant downside in terms of environment. The residues are as much as the energy crop potential that we think we could do if we put all arable land into energy crops. And so to me, the fairly obvious initial target should be these residues, not energy crops, where there are a lot of significant environmental and economic issues associated with energy crops as well. So if we come to negative CO2 emissions, this is going to inherently involve carbon capture. It will also, if it can involve a ubiquitous source of energy that you don't have to pay for example, sunlight, then you can actually get to a point where you can do negative carbon capture. So in the very broadest sense, you say, how important is it to actually get to negative carbon capture? Well, in the broad sense that negative carbon capture represents very highly efficient carbon capture, I would say it's essential. I think the kind of 90% nominal target that we talk about for capture from coal-fired systems is an arbitrary and poor choice of a target. That is, the last 10% of the CO2 that's in that stream is going to be far, far cheaper to capture than any other source of CO2 that's being emitted from, for example, transportation systems or other kinds of things. So the idea that we stop at 90% after having made the investment to get to 90%, the incremental costs of going to 90% to a very high capture efficiency are much, much lower than the cost is going to be, for example, for capturing an equivalent amount of CO2 from automobiles or especially from airplanes. But what if we take the narrow definition? How important is it that we actually become negative in the absolute sense of the word, that we're capturing more CO2 than we're producing? And is that even really possible? And I'll show you some scenarios here, I think, that will show that it is potentially possible and might even make some good sense sometimes. So let me start with the efficiency issue. These are actually locally sensitive data here. What you see in blue here are the normalized efficiencies of however many there are, 25 or so, dedicated biomass-fired power plants, most of them in the state of California, a couple from Canada and other places. So there are 73 of these plants in the state of California. I've done field tests in most of them, and you can see that their efficiencies, normalized by the coal efficiency, as you see here in blue, range anywhere from about half to and these are the most efficient of the 73 power stations, so anywhere from half to 3/4 of the efficiency of a coal-fired power plant. If, however, you take that same amount of biomass and put it into a coal-fired power plant and were to fire it with the coal-fired power plant, so it turns out it's not quite as efficient. Biomass is almost always more moist than coal, and that has an effect on efficiency. But if you were to do that on a long-term sustained basis and put all of the changes in efficiencies associated with having to handle and deal with moisture in the biomass would be burning with about 95% of the efficiency of a coal-fired power plant. So to put that in realistic terms, in absolute terms, if you co-fired a modern supercritical boiler with biomass, you'd be converting the energy, chemical energy in the biomass into electricity with about 40% efficiency, just under 40% efficiency. So one of the questions you have to ask is if that's a realistic option for a source of biomass, any other process that we look at ought to have to compete against that 40% efficiency in order to make sense. And if it's not competing well with that 40% efficiency, you've got to have a pretty good justification for why you would do anything else with that biomass. Because as we saw in the beginning, the limitation for doing any kind of negative carbon capture is the supply of biomass. And so the most important thing is to convert that biomass with the highest possible efficiency to whatever it is you're doing. That's going to be the most sensible use of the biomass. Now, if you were to go through all 73 of these boilers and calculate the average efficiency, the average chemical energy to cycle efficiency, the average chemical energy to electricity efficiency of 73 commercially operating biomass power plants in the state of California, on average, is 11%. So there are many of these that have appallingly low efficiencies, and they're fairly inherently less efficient than coal-fired power plants because they're much smaller, and because they're smaller, they can't be built with the same kind of reheat and recycle loops that you can with a large-scale coal facility. And furthermore, if you look at the cost of electricity from those systems, especially those that operate on seasonal values, the cost of electricity are very high because you have to pay for the capital of the whole plant, and you're operating it sometimes only a third or at most a half a year in some cases. All of the ones that show up here operate all around the year, but some of them are seasonal systems that don't. So I'm going to give a couple of examples of some technical issues that are critically important, I think, in implementing coal fire. So in general, if you mix the biomass with something like coal or some other reasonably similar product and convert it in either a gasifier or a combustor, that's going to be a much more efficient process, and it's going to be a much more economically efficient process than any dedicated biomass system would be. But it's not that it doesn't come with issues. So there are fairly significant issues in co-firing biomass with coal, and I'll point out a few of those in some detail. There are a lot more than we can talk about here, but just to give you some ideas of some of them. So in broad issues, if you're co-firing it, there are fireside issues, that is, in the boiler. So so I'll take a guess that there might be at least some people in here that aren't too familiar with how electrical power is generated from coal-fired power plants. So to put this in perspective, in a typical pulverized coal-fired power plant, You create a fireball that's roughly the diameter of this room and 10 stories tall, and that's inside of a 30-story building, and it's being fed coal at anywhere from many tens to a few hundreds of tons per hour. And so these are very large-scale operations, and what you're trying to do is feed some amount of biomass into that system. So how much biomass do we have? There have been a lot of estimates, but I would guess that an upper limit of the amount of biomass we have in terms of its thermal energy compared to coal is about 10%. So if we were to do this uniformly in all power plants across the country, we would maybe get 10% of the total thermal energy in the power plant in the form of biomass. The rest of it would be coal. So you're putting a relatively small amount by energy into this large conversion facility, but by volume, that turns out to be more than half of what's going into the power plant, because the biomass energy density is less than 10% of that of coal typically. So on the fire side, there's pollutant formation issues, carbon issues, there's big ash management issues, potentially very big corrosion issues. And then outside of the firebox itself, there's fuel supply and storage preparation, and what you do with the byproducts, the ash utilization and other kinds of things. And all of these have been looked at. There are solutions to all of them. However, if you don't do a clever job, and if we don't develop the tools to do a clever job, some of these can be devastating to the operation of the rest of the power plant. And I'll give you just a few examples of that. So one of the first examples is corrosion. Most biomass fuels have a fairly significant amount of alkali material in it, typically potassium, sometimes a little bit of sodium, and commonly a fair bit of chlorine. And in particular, the faster the material grows, like an energy crop, and the more actively growing it is when it's harvested, the higher the concentrations of those are, because the potassium, usually in the form of potassium chloride, is what's responsible for transpiring the water through the biomass and getting the biomass to grow, bringing the nutrients through it. So when you burn the material, the potassium chloride forms a vapor, a potassium chloride vapor at the high temperatures, but at the relatively low temperatures of the heat transfer surfaces, it will condense to form a solid. And you can see that in this slide. So this is a steam tube, simulated steam tube, and a boiler that has an ash deposit that's grown on it. And we look carefully on the surface, and you can see there's a chlorine layer there. This is the iron that's part of the tube itself. And even in this case, just a couple of hours of exposure, you can see that this chlorine has started to pit and corrode that iron layer. And it has been the common experience of people using biomass that if you're not careful about the type of biomass and its properties that you use, you can corrode out the components of your billion-dollar boiler that's designed to last for 20 to 60 years in about a year, or sometimes less. And so that's a pretty major problem and just a practical problem. If, however, you blend that biomass, in this case, this is wheat straw from Imperial Valley here in California. If you were to blend that straw with a fairly typical coal, turns out the chemistry of the coal and the biomass help each other out in this case. The biomass actually captures some of the sulfur from the coal, helps to capture the sulfur, and you can see the evidence of that here. The chlorine is gone, the corrosion is gone, and the potassium has formed a potassium sulfate layer instead of a potassium chloride layer on that surface, which is far less corrosive. It's still somewhat of a problem, but far, far less of a problem than the potassium chloride. So understanding in detail these kinds of interactions are some of the kind of fundamental important issues that need to be understood. For example, if this were a gasifier instead of a combustor, this would not happen. The potassium chloride would not form a sulfate, and you would still have the corrosion problems in here. And understanding those kinds of details is just one example of some pretty critically important stuff. So this, when I looked at this just beforehand, I didn't choose a very good biomass particle, but the principle here is the same. So coal particles, when coal is burned as pulverized coal, which is about the size and consistency. It's almost as fine as household flour, not quite, but considerably finer than sugar or salt, for example. And biomass cannot possibly be made to that same size. And so to try to get biomass down to that size would take an enormous amount of energy. Nor is it spherical. And so this is just an example of looking at biomass particles with a camera, and we've been able to develop a way of getting a pixel by pixel indication of the temperature of the surface of that particle, and then recreating the three-dimensional particle and getting an idea that these particles don't burn anything like coal particles, and understanding that is a fairly critical issue. Also looking at, these are some of the first data I think ever collected of this type. These are commercial scale, near burner measurements of the flame structure in a real commercial application of biomass co-firing. and understanding the dynamics of that flame are also pretty important. So there is a huge amount of very fundamental work that needs to go on to make these systems really work well. But the practical application of putting these into kind of existing technologies is pretty important. If we move on to carbon capture, this should be for most people here kind of old news. So this looks at so what this slide shows is the impact of carbon capture systems on the efficiency of a power plant. And the bottom line is the efficiency drops by somewhere between 25 and 30% by most carbon capture systems that you apply to a carbon plant. So doing the carbon capture consumes something like a fourth to a third of the output of a power plant just to do the carbon capture on the system. That's a huge penalty from the standpoint of practical things. If you look at the impact on costs, these on the left are showing costs without carbon capture, and this is costs with carbon capture using several different technologies. And the bottom line here is that you increase the electrical power generation cost by about 80% by doing carbon capture for most of these systems. We've developed a system, let me just back up to say that system says if we were to build 2 power plants with the same output and compare their operating costs, that's what the way the operating costs would compare. But a more realistic way of assessing cost is to say, if I were to take my existing fleet of power plants and implement carbon capture, how much would that change the cost of electricity? Instead of being an 80% increase, that would come out to be something more like a 500% increase because of the sizable amount of additional capital that you have to invest in modifying the existing plants. So you're not building them all over again. If you do have to build them all over again, then you're looking at not just the cost of implementing carbon capture, but the cost of replacing the existing plant as well. And that's a much, much larger cost. And so that's actually far more significant than the carbon capture cost directly. So this is a process that we've developed that at this point I would say has been demonstrated and verified, including by Fluor, who are the purveyors of the principal competitor to this technology. They were in my office the other day and they said there's no way they can compete with this process. And how can we talk to you about how we're going to do something together? So this is another carbon capture process where it can be implemented in a couple of ways. You basically modestly compress the flue gas, put that through a series of heat exchangers, expand it again, cool it down to the point where the CO2 desublimates. You separate the solid from the gas, warm everything back up again, and you end up with a CO2 stream and a gaseous stream. You can do that also in another version of the process that doesn't require either compressing or expanding the flue gas, which makes the equipment a little easier to specify, but the process gets a little bit bigger. And I'll just go to the energy costs here. So energy is a fraction of the output of the power plant. These are the alternatives to this process. This process can reduce the energy demand of carbon capture by roughly a factor of 2 compared to the other kinds of processes. And the costs, the levelized costs, are also reduced mostly by about a factor of 2 for doing this. And fairly significantly for the point of this conference is, unlike most of these other processes, you can push this to extremely high capture efficiencies and still be relatively economic. So this shows the specific energy, the amount of energy per ton of CO2 as a function of the CO2 capture efficiency. And it's not until you get to about 99.8% capture of CO2 that these costs start climbing very steeply. So you can, and it only takes, at 99.5% capture of CO2, you're actually capturing all of the CO2 that came from the coal, and you're starting to capture CO2 that started off as part of the gas that came into the power plant. So I was going to show you a slide, but I think we're going to be out of time. So this is just a picture of this process actually running. We've built this at several scales now. So there's a video in here that I won't take time to show you right now, but it shows the process really works and it really does run. Some empirical data showing both long-term storage and also fairly significantly this, whoa, I've got some sympathies. I don't know what happened there, but wow, there's another one. So this captures not just CO2, which you can see here. So depending on the temperatures that you achieve in the process, you can capture CO2, but you also capture SOx and mercury and almost every other pollutant. Not every other pollutant. It does not capture NO, but it captures most of the other pollutants better than existing control technologies can capture them. And if you try to apply this line would correspond to coal combustion, but if you look at other kinds of systems that don't have as high of CO2 concentrations, you can apply this fairly broadly over a broad range of natural gas, other kinds of systems that work very well. So in conclusion, There are some very practical ways, I think, where you can achieve negative emissions. I think this new carbon capture technology is one of them. Co-firing biomass with coal and adding carbon capture to that is another one. And they make a lot of sense both economically and from a broad process perspective. I'm not too sure that actually achieving negative, I'm pretty sure it's not going to be possible to get an average CO2 capture that's negative. But at least on isolated conditions, it actually does make economic and process sense to do that, where you can co-fire biomass with coal, for example, in either a gasifier or a combustor. There are a lot of examples of that. The final thing I'd like to say is that the only reason that we're really talking about any of this is to actually try to do something about the climate. And when you look at the quantity of CO2 that we have to capture in order to have any kind of a realistic impact on the climate, it's actually imperative that we go to very high capture efficiencies. I'm not sure that it's imperative that we go to uniformly negative CO2 emissions, but you have to go to significantly higher than 90% capture efficiencies on any stationary source, because the realistic ability to do things with large, heavy loads like trains, planes, or trucks, you're just not going to get that high capture efficiencies there. So I'd like to acknowledge our graduate students who do most of this work, and Sustainable Energy Solutions who does the rest of it, and our sponsors, and be happy to answer any questions for them.
Yes, how does the cryogenic capture work on natural gas fired, where all you got to do is, and also oxygen natural gas fired, where all you got to do is condense the flue gas and you got 100% carbon dioxide?
Yeah, so if you have an oxygen natural gas system, then you've invested the energy and the capital up front in the air separation unit to do the CO2 capture. And so if you've already built that system, it wouldn't make sense to do a separation process downstream. You just have to condense the water and you've got a CO2 stream. So, but if you're doing an air natural gas system, this is considerably, so the issue there is that the cost per ton of CO2 increases as the concentration of CO2 in the inlet decreases, right? But in this particular technology, that increase is very marginal until you get down to 1% CO2 or something like that. And so it's actually quite effective. The easiest way to think about this is this. If you can afford to do an air separation unit before a combustion process, which actually has to treat a larger volume of air and get to a much colder temperature, then you certainly can afford to do a post-combustion cryogenic system, which doesn't have to get nearly as cold and actually treats a smaller volume of air, and it uses essentially the same technology. There are some important differences, but the conceptual flow diagrams are reasonably similar. And so that's perhaps the one-sentence version of why this, fairly compelling version of why this approach would make sense.
Yeah, thank you for your talk. I had a question about when you're looking at different co-firing blends where you're looking around 15% biomass, and also if you looked into any of the pre-treatment options and how those would affect the pulverization characteristics, so like torrefaction or something like along the scale to charcoal, where you could get smaller particles and, you know, different dynamics there.
Okay, so those are both great questions, but completely different. So let me answer both of them. First of all, so you can do co-firing up to, people have demonstrated co-firing in individual burners of a boiler on a sustained commercial basis of 50% fairly routinely. But for a large coal-fired boiler, you would be very, very hard-pressed to get enough biomass to the system to get even up to 10% of that system. So practically, for large-scale implementations, co-firing will be done at 10% or less probably, unless you have either a small boiler or a phenomenally large supply of biomass for some reason. So the issue of torrefaction or other pretreatments are, if you look at the economics of the situation, the most important thing you can do to make the process as economical as possible is to touch the fuel as little as possible. So ideally, you pick it up in the field once, and the next thing you do with it is put it in the boiler. And so any kind of processing steps that you do between there making, so it's already marginally economical, probably not economical even, but fairly close to economical the way it is. And anytime you touch it or do anything to it, you're making the economics a much more difficult proposition. So you can make the handling much easier, but the overall economic performance is poor when you do that.
Okay, I want to thank you again. We actually do need to move on, but we'll carry on the discussions over lunch. Thanks.